I already talked about the electrical location of overcurrent protection devices. Let's talk a little bit about their physical location now. Start off, we'll talk about junction or pass-through boxes. Now, these are typically an enclosure that allows for electrical connections to be made, and it's usually used to transition wire types. These are very common in especially residential systems, smaller systems. They are used to, for instance, switch over from PV wire that's used to wire the array in free air behind the modules to THWN-2 running conduit to a disconnect switch or combiner box or inverter or whatever it may be. These do not have overcurrent protection devices in them. That's kind of fundamental to the idea here. As a junction box, it's not holding overcurrent protection devices. These are not fuse holders. Those are terminal strips where we just terminate wires and connect them together and continue on that circuit. Here's another example inside a PVC enclosure. Same thing going on. Wires coming in from the array and then going out to the next piece of equipment in the circuit. Combiner boxes, something that we use on all sizes of systems, not all systems, but all sizes ranging from string inverters up to large central inverters, are defined in 690.2. This is an enclosure where multiple PV source circuits are combined in parallel and they form a PV output circuit. So we've looked at examples of this already. We've kind of talked around it. It's important to keep in mind that these definitely are going to have overcurrent protection devices in them, because we're making that parallel connection unless there's only two strings, right? We've talked about that already. We could have a combiner box where we connect two strings in parallel. There's not a source of fault current or overcurrent there. No overcurrent protection devices required. Much more common, though, is for there to be fuses in the combiner box. Also, we may have an integrated disconnect. You can see here that somebody's using this disconnect switch, which has a handle on it when the door is closed, as a hanger for their meter as they're checking voltage on these fuse holders for these PV source circuits. They have to be listed. Combiner boxes are required in 690.4b to be listed to UL 1741 for the application. Back in the day, we used to make our own combiner boxes, kind of build them from parts and pieces. That doesn't fly anymore. These have to be specifically listed for the application in accordance with UL 1741. So all kinds of shapes and sizes of combiner boxes out there, ranging from just a couple strings up to, I've seen way bigger ones than I ever hope to see again on some older systems out there. But, 24 or 32 string combiners, very common on larger systems that use central inverters. Now, sometimes these series fuses are not in combiner boxes. They're kind of in a combiner box, but they're really integrated into the inverter. Right? So very common with string inverters. We've got our actual electronics cabinet here, and then down below we've got the wiring cabinet, which has usually terminations for both the AC conductors, you can see those here, as well as for the DC conductors. And that's where the series fusing is likely going to live if we have an inverter with an integrated combiner and series fusing going on. Now, you want to make sure that when you're using these, a lot of times they come with fuses from the manufacturer. You better make sure that's the right size, or you better order the right size. Maybe you got 15s and lo and behold, you need 20s. Or maybe they're 20s and you want to use 15s. Or maybe they didn't come with any fuses. I've seen ones where they don't put a fuse in there. They just put a slug, a piece of metal that is basically a conductor and provides zero overcurrent protection. So always make sure they're the right size for what you're doing. The manufacturer doesn't know. They don't know what array you're connecting to this thing. They give you the guidance in terms of what the voltages need to be and what kind of current the inverter can handle, but they don't know what modules you're using or how many of them, how many in series, that kind of thing. So make sure that you verify that size that's supplied. In some cases, we run into situations where we use an external combiner box due to the layout of the system, whatever it may be, and we want to bypass the internal integrated series fusing in the inverter itself. Right? We want to, instead of running a bunch of PV source circuits in, we're just going to want to run one in, and it's the combined output of all of these strings that occurred out in the array field somewhere, and I want to connect to where all these things are connected, to the bus bar on either side of these. Again, this is a fuse holder or an inverter that's got fusing on the positive and negative. As we mentioned, only required on one polarity earlier. We can do it on both, and there is a lot of equipment out there that is still doing it on both. We will probably see that change over time. But if I don't want to use these and they're there, I need to be able to bypass them some way. That is possible with some equipment. Others, not so much. Some inverters you can order with the integrated combiner or without it. And in some cases, you can order it with a wiring cabinet, but without fusing in it. And it may just have a single larger terminal for connecting a PV output circuit to the inverters. Always got to look at how those things are configured, look at what your options are, and make sure they're going to work with the array that you want to connect to it. What about recombiner or subcombiner? We've kind of mentioned this a little bit already. It's really a trade word or a slang word. It's not defined in the NEC. It's really just another DC combiner. We bring in multiple PV DC circuits, we combine them in parallel, and have a larger, higher current circuit leaving that combiner or recombiner. In some cases, we come into a recombiner, multiple circuits, they go through a fuse and a disconnect, and then they run on individually to an inverter where they're combined on the bus bar of the inverter. It all depends on the layout of the particular system. But it is a parallel connection point for multiple PV output circuits fundamentally. So it's just a higher level of DC aggregation on a larger scale system, right? Often these are going to be integrated into the inverter cabinet. As you can see here, we've got our overcurrent protection for each of the PV output circuits. We've got disconnects for each of them built in as well. And, these are maybe 250, 350 amp fuses. They're connected on the array side to like a 24 or 32 or 40 string combiner, or whatever it may be. I don't know. I'm sure of the specifics on this one, but that's the point. This could be in a separate enclosure adjacent to the large inverter. It may be integrated into it. You may have options. Again, it's going to depend on the array and the configuration. And usually these kind of details is really important to specify them when you're ordering these large pieces of equipment, because again, the manufacturer doesn't know how you're configuring it. You may have the need for some 250 amp fuses, some 300, some 350s because of the way the array is laid out. That's all got to be coordinated and often specifically ordered when placing the order for the equipment. Okay, let's look at another schematic here. 3 PV source circuits. In this case, we've got inverter integrated series fusing and a DC disconnect. We know with crystalline silicon modules, we can usually put 2 PV source circuits in parallel without fusing. Once we get to 3, we're typically going to need it. So here we've got our strings on the roof or on the ground or wherever they are. They're running through to some kind of junction box or pass-through box. We make a wire transition in there, typically PV wire or USE2/RHW2 that's also sunlight resistant. And then we're transitioning to some type of conduit-ready wire. Often this is going to be less expensive than this wire here, so it makes sense to use it. It's also typically has a smaller diameter, so we are able to use a smaller conduit size than if we use the PV wire. But not always. That's not always the case. If we're running 1,000-volt circuits, a lot of times we don't have conductors rated for that, or 1,500-volt, we may end up using PV wire all the way to the inverter. In this case, we're running the individual circuits all the way to the inverter. Each one terminates on a fuse that's in series with one of the polarities. So if you can see the presumably positive wires, they're red, each connected to a fuse, output of the fuse connected to a bus bar. All of the negative wires are connected to a single bus bar. And we've got an integrated disconnect in the inverter, which switches both of the polarities. So we'll talk about disconnects elsewhere, fusing on one polarity, disconnect on both on the DC side. Looking quickly at the AC side, there's our ungrounded conductors, line 1 and line 2, solidly grounded neutral conductor here running all the way back. We've got a disconnect switch on the AC conductors. And then at the point of interconnection, where we're connecting the current limited output of the inverter to the primary power source, the much larger current source, we've got a breaker in series with each ungrounded conductor at the point of interconnection in that AC panel. Similar setup. Should have mentioned on the previous one, you probably figured it out. We're not looking at the grounding here, focusing on fusing, talking a little bit about disconnects. Pretty similar setup, except in this case, the combiner is external to the inverter. It could be right next to it. It could be on the roof. It could be wherever. It doesn't matter, but it's not built into the inverter. The inverter does have a disconnect built into it. See the switch on both polarities. And in the combiner box, again, we've got fusing in series with one of the DC polarities. Got to be the same, so on all the positives. All of the negatives run to a DC bus, continue on to the inverter. AC side, same as the previous. We've got our overcurrent protection at the point of interconnection, where a current limited circuit is being protected from the larger fault current and current availability from the primary power source, the utility grid, whatever that primary source is. Okay, we're going to talk a few more OCPD examples in the last part of this presentation. I will see you there.